This is Physics Lab 2, Motion of a Falling Object. Here's a quick rundown of what we'll be going through today, and let's start with an introduction. So what is the purpose of this lab? The purpose of this lab is to measure the motion of a falling object dropped from rest, and this is to explore the relationship between gravity, drag, and net force. Falling objects only have two acting forces on them, gravity and drag. However, because these forces are not equal and opposite, they have a net downward force. And this also plays into Newton's second law, which states that objects with acting net force will display a change in velocity. Next, here are some formulas that will be used. The velocity update formula and position update formula will be used in the computational models. Force to gravity is displayed by Fg, which is negative mass times gravity, and the drag force is represented by negative b, which is proportionality constant times velocity instantaneous squared. Let's take a look at the observable model. So here, this is the video of me dropping an object with drag force. And as you can see on the right, graphs of the velocity and position are displayed, and these starting values will be used to calculate the computational models. So as you can see, the gravitational model requires a few inputs. First, the mass of the object was 0.136 kilograms, and the starting position vector was 0.567 in the y direction. And as you can see, based on the placement of our axis, the object will move in a negative y hat direction. Similarly, the j hat vector is represented as -1 to show that it moves in the -y direction. Next, for the calculation loop, we change this value to represent how much time passes during the course of the object falling, and these formulas come from the velocity update formula. And here we can see, once all these values are plugged in, we get a pretty similar trajectory to what was shown in our observable model. Likewise, in the drag force model, most of the inputs remain the same. However, we do have to update the b constant, which is the proportionality constant, which is calculated by running the observable model until the end position is reached. Also, the same formulas are used, position update and velocity update. And this is what it looks like. As you can see, there's a position versus time graph and velocity versus time graph. So, results. How do these three models compare? As you can see in the blue, the observable model has arc-like trajectory. In the red is gravitational, in the yellow is drag force, and as you can see, drag force is much more comparable to the observable model than is the gravitational. And this is true because in real life, air particles resist the motion of a falling object, and therefore it closely resembles the observable model. Lastly, here are some discussion questions. Which models, if any, predict the terminal velocity? So in the gravitational model, terminal velocity is not reached because velocity will continue to increase and accelerate because there is no opposite force in the positive y direction. However, in the drag force model, terminal velocity will be reached because acceleration will reach 0 at some point. As you can see, the slope is curved here. However, it is not curved it is a constant slope in this model. If it was initially thrown downward, would the terminal velocity change? No, because initial velocity will not affect the slope of these models. Thank you.